This is the fourth in a series of videos about simple electronic components. We'll look at capacitors here. A capacitor is a device for storing charge. It consists of parallel plates of conducting material separated by a very thin layer of insulating material. This insulator may contain polar molecules or functional groups that can reorient themselves when placed within an electric field. Such an insulator is called a dielectric. The voltage that builds up between the plates is related to the charge stored on the capacitor. The relationship is usually expressed Q equals CV. The proportionality constant C linking the charge and voltage is known as the capacitance of the device. The larger the capacitance, the larger the charge that will be stored on the device at a given voltage. The standard unit for capacitance is the farad. 1 farad equals 1 coulomb of charge per volt. In practice, a coulomb is a lot of charge, and a farad represents a huge storage capacity. Capacitors with ratings of microfarads or even nanofarads or picofarads are common in practical circuits. The capacitance varies with the physical size. A greater amount of charge can be stored the larger the area of the plates. Rod-shaped capacitors are actually made from a dielectric film sandwiched between pieces of metal foil and rolled up like lefse roulade. Here are some examples of commercially available capacitors. There is essentially a non-conducting gap between the two leads of the capacitor, so it may seem surprising that capacitors can carry a signal from one lead to the other. Although there is no continuous conductor, the two plates are close enough to each other that the electric field created by the charge on one plate induces charges to move or rearrange on the other plate. An excess of electrons on one plate will repel a proportionate number of electrons away from the surface of the other plate. The net effect is that current appears to move through the device up to a point. Recall that whenever we have a difference in the concentration of charges between 2 points, we have a difference in the electrical potential energy between these 2 points. That is, a difference in voltage appears. If we are using a battery to push charges onto the capacitor, then a voltage builds up on the capacitor until it eventually is equal to that of the battery. At that point, there is no net force to drive more charge onto the capacitor. Consequently, the current stops once the charge builds up. If we were to open a switch between the battery and the capacitor, that charge would be trapped or stored on the capacitor. There are some important consequences here. If we are using a big enough capacitor, the amount of charge can be dangerous to people and to electronic equipment. Accidentally touching your hand to the lead of a fully charged capacitor can unload a dangerous level of current through your body, so be careful with big capacitors. Something of this size could discharge enough current to hurt. A capacitor this big could really be dangerous. This charge trapping approach can be a useful way of capturing or sampling a signal by charging up very small capacitors until the voltage between the plates matches the voltage on the signal source. Then breaking the circuit with the signal source allows us to hold the voltage equivalent to the signal at that moment in time. In a sense, this is a snapshot or sample of the voltage signal at that particular time. This is called a sample and hold technique and is frequently used to give us more time to measure and store the value of the signal. The relationship of current and voltage associated with a capacitor is different from the relationship of current and voltage across a resistor. There is a time dependence that is unique for the capacitor. This might be best illustrated by the simple circuit here with a battery, a switch, a resistor, and a capacitor all in series. Let's do a thought experiment in which the switch is initially open. There is no current flowing in the loop, so there is no voltage drop across the resistor. Let's also assume that the capacitor is not storing any net charge to begin with. Now we close the switch and current begins to flow. The capacitor begins to charge up. While there is current in the loop, there will be a voltage drop through the resistor. so its value will be I times R. We can think of the capacitor and the resistor together as a voltage divider. The battery voltage is divided between the voltage on the capacitor and the IR drop through the resistor. It takes a little time to charge the capacitor, but as the charge grows, the voltage increases as well. Less voltage is being dropped than across the resistor. At time 0, the voltage on the capacitor is 0. When the switch is closed, charge begins to accumulate and the capacitor voltage begins to grow exponentially until eventually it reaches the same voltage as that of the battery. The voltage across the resistor is complementary to that of the capacitor, since their voltages must sum up to the battery voltage. So the voltage on the resistor follows this curve. It is initially equal to that of the battery and then drops to 0. Both of these curves are an exponential function of time. If you think this looks very much like the products and reactants of a reaction mechanism that follows a first-order rate process, then you're right. The rate constant K can be shown to be equal to 1 over R times C. The product of RC is known as the RC time constant for this circuit and has the units of seconds. Soon after closing the switch, all of the voltage appears across the resistor. At very long times, such as 5 times the RC time constant, virtually all the battery voltage appears across the capacitor. The larger the value of RC, the longer it will take the capacitor to charge. This time-dependent behavior has some very practical applications. Besides being used in timing devices, this type of RC circuit can be used to filter or exclude noise that varies rapidly with time. For example, let's imagine that we're monitoring a signal from a liquid chromatograph in the form of a voltage. The signal that we are interested in changes relatively slowly with time. A peak takes several seconds to rise and fall again. However, the environment we're working with might also include electrical noise that varies at very high frequencies. We want to exclude this noise so it doesn't obscure our chromatographic peak. Here we can use a simple RC circuit in which the voltage signal from the chromatograph replaces the voltage from the battery. We want to prevent the very rapidly changing voltage associated with noise from going on to our computer interface, but still allow the relatively slowly changing signals from our instrument to get through. Here is the key idea. A very rapidly oscillating voltage changes direction so quickly that the charge on the capacitor can't keep up. It will drive the current through the resistor first in one direction and then in the other, as though the capacitor wasn't even there, and we have a direct connection or a wire from the signal to the resistor. Essentially, 100% of these rapidly changing voltage components will appear as a voltage across the resistor and contribute nothing to the voltage on the capacitor. We say that the capacitor passes only the low-frequency components in the signal. By measuring the signal across the capacitor, we create a low-frequency or low-pass filter. If, on the other hand, we are interested in only the high-frequency components of the signal, we can exclude these slowly changing components by measuring the voltage across the resistor. This situation provides for us a method of capturing the high-frequency components, and we call that a high-pass filter. So a simple take-home message is that a capacitor looks like a direct electrical connection, essentially a wire, to any rapidly changing signals, but an open circuit, or no connection, to slowly changing signals.